Now let's introduce an example that has some springs in it. So imagine I have two particles. So one is particle P, and it's attached to the wall as such. And then we have another particle Q that's attached to the wall via a spring. And then we have a massless rod with a length L that links these two particles together. And both of these particles have a mass of m. And just a few other notes that the resting position, or so the unstretched, both strings are unstretched when the rod is completely vertical. And so with that, I'm going to, and the point P and point Q can only move, so point P can only move in the horizontal direction, and Q can only move in the vertical direction. Okay, and so with that, now I'm going to define our reference frame A, so I'm going to call that O. And so we have A1 here and A2 here. And I'm going to call this distance here X, and this distance here Y. And so let's draw the free body diagram for each of these particles. So if we have Q here, we have a spring force, I'm going to call that FSY, acting to pull Q up. We of course have gravity acting in the vertical direction. We have a tension in the rod here. And then we have a normal force acting right on point Q. Imagine there's a wall here and a wall here, and this is just to keep the particles from moving either in the vertical, Q just in the vertical direction, and then P just in the horizontal direction. And now if you look at particle P, we have a spring force acting in this direction here. We of course have the mass, or the gravitational force in this direction. We have a tension force here, and then we also have a normal force acting in this direction. I'm just going to write this as NQ and P to distinguish. And so again, we have a mixture of conservative and non-conservative forces. So conservative forces being gravitational forces and spring forces, and non-conservative ones being the normal and tension forces. But if you look at the directions of normal and tension, there's no movement in those directions. So therefore, the work done by those forces is zero, and that means we can, again, use our conservation of energy approach. So we can use the following equation. So we'll start with kinetic energy. So the total kinetic energy is equal, we have two particles here, so we have 1/2 times the velocity of P squared plus 1/2 m times the velocity of Q squared. So the position of P is equal to xa1, and the velocity of P then is equal to x dot a1. The position of Q is equal to ya1, and then our velocity is equal to y dot. Oops, sorry. This is a2. a2. So we can plug those into our equation here. So we get 1/2 m x dot a1 squared plus 1/2 m y dot a2 squared, which then gives us 1/2 mx dot squared plus 1/2 my dot squared. So that's our kinetic energy. So we can start by writing, first of all, defining where our position, our reference height, so where potential energy is going to be equal to 0. So we're going to call that here, PE equals 0. And so our potential energy that's going to come from the gravitational force acting on Q is equal to mgy. Now the gravitational force that's acting on X, well, the location of X is already at the 0 potential energy point. So in essence, that would be the same as saying Y is equal to 0. So we don't include that term here. Next, we have to consider the spring forces. So if we look at our spring FSY, so the one that's attached to Q, we have 1/2 K, and the resting length of that spring is equal to L, and then the displacement, right? So basically, this displacement here is equal to L minus Y, right? And so that's why we get L minus Y over here. And then we have the force from the horizontal spring. So that's going to equal 1/2 K. And its resting length is, is when this is vertical. And so when you have this displacement here, that's the displacement we're going to multiply K by. So that gives us K x squared. And so you take these two equations, so the one for the total kinetic energy and for the total potential energy, you set them equal to a constant. So what you get is 1/2 mx dot squared plus 1/2 my dot squared plus mgy plus 1/2 k L minus y plus 1/2 k x squared. And that's going to equal, I'm just going to draw it over here, some constant. And when we take the derivative, right, so now I'm just going to write this here. We're going to take the derivative of both sides, so d dt and then d dt. So what you're left with is mx x double dot plus my y double dot plus mg y dot minus, oops, sorry, this also should be a squared up there, minus k L minus y y dot plus k x x dot equals 0. Okay, so we have one equation of motion, but you may notice that we have two unknowns, x and y. Well, if you remember back to a few weeks, it turns out that actually we only have 1 degree of freedom in the system, and that is because the attachment, the fact that Q and P are attached by this rigid rod, introduces a constraint. And so we only have 1 degree of freedom. And our constraint equation is x squared plus y squared is going to equal L. And so we can use this equation and then plug in these terms to put everything in terms of one variable. And so I'm going to do that and put everything in terms of y and its derivatives. And now some of you caught on to the fact that you could do this. I initially introduced when you're working with constraint equations to encounter or incorporate the constraint immediately when you're working with your position vectors and such, so all the way up here. But here, for sake of ease, I went through everything as though they were uncoupled or unconstrained, and now we're going to implement this constraint. So we have that to put everything in terms of y, we're going to write our constraint equation in terms of x. So we get x is equal to the square root of L squared minus y squared. And I'm just writing what these derivatives were. He went through how to calculate them in prior examples. So this ends up being negative y dot over the square root of L squared minus y squared. And then for x double dot, we end up with negative y dot squared over the square root of L squared minus y squared plus negative y double dot over the square root of L squared minus y squared plus y squared y dot squared over the square root of L squared minus y squared to the third. And so we can plug these terms into this equation here. So x double dot, x and x dot. And so now that I've cleared some space, I can actually write out what our equation of motion is in terms of y. Remember, you can also write this in terms of x if you wanted, but here I am doing it in terms of y. And I'm just going to write what the final solution is. You can see how you arrive at this in the notes that are provided. You get mg minus kl plus my y dot squared. Make sure that's clear what's a actual dot. So y dot squared over L squared minus y squared plus y squared y double dot over L squared minus y squared plus my to the third y dot squared over L squared minus y squared squared, plus you have this I'm just writing it over here for space, y double dot, and this is equal to 0. And so this here is your equation of motion. Now, in the written notes, I also provide the derivation of this equation of motion using the linear momentum and force relationship. And so you can go through that yourself and compare what you think is easiest. Again, it doesn't matter what method you use to get the equation of motion. What matters, it will always be the same.